Yeah.
So we've got our graph. Figured out that all the points that are exact, that work perfectly, they add up to exactly $1,280, make a line. We're going to do something. There's a mathematical way to represent the points that work and don't work. And you guys noticed a minute ago that all the red points that didn't work were above the line and all the green points that worked were below the line. You guys marked some of the green points. Are there more?
Yes. Yeah.
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 There's a bunch more down here, right?
Yeah.
Mathematically, there's a way to communicate that anything below this line is going to be a combination that works. And the way we communicate that on a graph mathematically is by shading that side of the graph. So you can add in some shading on your graph.
And I love it.
So again, what the shading means is that anything in that piece of the graph is something that will work. It puts us under budget for our pet sitting business. So we could pick other points in here other than the green points you marked, and those points would also work. That means that if I can find the boundary line, then I can figure out from there where the rest of the points are. We've been reviewing how to graph a line. So this is kind of a two-step process. If I gave you another problem like this and said, make me a graph of where all the solutions are, you could do a couple of steps. Your first step would be to graph the boundary line.
We cannot see.
You can't see on the video. Doesn't see.
We cannot see.
The video isn't showing
You
what you're
can't
writing.
see it.
You can't. You know?
Here we go. Notice. Help our friends that aren't gone. We have a few people absent today.
Cool beans.
We can also go like this. There. Okay, so graph the boundary line. Normally, if I tell you graph this, what am I going to give you if I ask you to make a graph?
Points.
What are you going to use to get the points?
An equation.
Oh, an equation.
I just said that.
So usually, you'll start with an equation and you'll graph that equation. You guys have been doing that a lot on your Ready, Set, Goes lately. There are a couple of different equations for this line. One of them came up on our 5.1. It got shared. And it has to do with how I get the total. To get the total, we have to do the total for the cats plus the total for the dogs, and it should make 1,280, right?
Yeah.
We can make an equation that says that.
Cool beans.
So I can do $32 times the number of cats. What am I going to use to represent the number of cats? Where is it on the graph?
Y.
And then I have to add that to the total for the dogs. The dogs are $80 each. I put them together, and it should make a total of 1,280, right? This is actually an inequality because I can be under budget, right? So instead of putting an equal sign here, what would be better?
Did you hear that?
A inequality sign.
Lily rolled up.
A non-equal sign.
Instead of putting an equal sign, what can I put here that says this could be anything as long as it's 1,280 or under?
Oh,
less than
equal.
There we go.
Lily's on her knees a lot.
So this is actually an inequality because I don't have to use all of the 1,280. I could be under budget as well, right?
Right.
Right.
You should.
Aye, Captain.
Are you ready?
As far as graphing this goes, in this format, a minute ago I asked you guys, well, how would I figure out if I had only cats? And you guys told me to just do the 1,280 divided by 32, and that gave me 40, right? I could also get the other end. How would I get only dogs?
Divided by
Same
80.
thing.
Divide by 80. So do you see how to get the two endpoints of the graph? I can look at just that, and then just that.
Yeah.
So that introduces an idea that we're going to work more with. That's an idea called intercepts.
No way.
You're finding the y-intercept and what's called the x-intercept, where we touch the x-axis on the graph. So that's something we're going to work more with. But you guys found those points, so I want to point it out. You could also make a slope-intercept equation for this. What was my y-intercept again? Yeah, 16.
16?
Yeah, 16.
And then,
Then you do plus 32.
do you guys remember rise and run?
Yes.
Sure.
Down
What's my slope?
2 over 5.
2 over 5.
It's rise over run, right?
Yeah,
Yeah.
it's rise over run, not run over rise. That's the
Rise
wrong
over
way.
run.
That just sounds so weird. What made you think that was a good idea?
Again, this is an inequality, right?
Mm-hmm.
This one, it's a little, if I'm going to put it in this format instead, it's a little bit harder to figure out which way to get the symbol. It's not as obvious like this where you've got the total and you know it has to be less than the total. This is in a different format, it's not the total. So if you know kind of what the equation is and you're not sure which way to put the symbol to make it work, you could always pick a point. So like somebody shaded 0, 0 as a point that worked, right? So I could drop that in really quick. 16 minus 2/5 times 0 is just 16, right? So 16 here, I would end up with 0 there. So that means I should put the symbol that way, right? Normally, you would be given the equation. So you can graph the boundary line given the equation, and then the next thing that you would do is we have to figure out where are the points that are over and where are the points that are under. The best way to figure that out is to do exactly what you guys did when you were collecting your data, and that's just to pick some points to test them out. So try a point. Is it over or under? And that'll tell me which side of the boundary line works and which side of the boundary line doesn't work. So pick test points. And you don't have to pick a bunch. It only takes 1 or 2 points for you to figure out which side of the line is going to work and which side of the line is not going to work. Pick test points and shade the side of the line that works.
Good chow.
Okay. Stop touching the water ball. Last comment on this. I drew a solid line through the points here, and that was actually intentional. And there's one thing you guys need to know, and it actually has to do with this. It's kind of another thing about graphing the boundary line. When we were doing inequalities in our last unit, we were graphing inequalities on number lines, right? And when we were graphing on a number line, we had a couple of things we had to keep track of. Open dot versus closed dot, right?
Yeah.
That idea still shows up here, but I have to represent it differently because now I don't have dots, I have a line, right? So a closed dot turns into a solid line. So that's why I drew a solid line through the points. So that tells me that everything under the line or right on the line will be within my budget. If I didn't want to include the points in the line, so if I only wanted the things that really are under the line, an open dot, then I could still draw the line, but I would have to draw a dashed line instead. So that's the connection between open dot and closed dot, dashed line versus solid line. That open dot, closed dot idea is still there on the graph. What you guys just found is a graph of a 2-variable inequality. And you just mathematically represented all the possible solutions to that. So all the possible solutions would be that shaded area. I can pick anything in the shaded area and it works.